Welcome back. Now we get started with Module 3. Now this module is all about security. But what does the title mean? Why shift security left? We'll explain this in a few slides ahead. Now please note that this is the third module of our session. Now our goal is not only to look at security, but also see how we can apply them to our modern DevOps practices, including containers. Now back to the question we had earlier. What is shift left? Now shift left and shift right refer to two different testing strategies. Imagine development as a horizontal line that moves from left to right. Shift left means to move quality-related tasks like testing to earlier stages in deployment, or so-called upstream. In traditional development, there is a tendency to push tests to later stages, or right. Example, after we have a finished product. And the reason to do this is pretty obvious. Traditional end-to-end tests often only make sense when the final version of the software is ready. But remember, in Agile, we value something that works over something that's perfect. In fact, often in Agile, we don't have a so-called finished product, but we just keep improving on it. This is why we want to shift left. Now, if you take a look at the diagram on the slide, the blue bars in the image on the slide, these are so-called the L0 and L1 tests, which are often referred to as unit tests. Now, they take up most of the testing instead of L2 and L3 tests, which are more like functional tests. And when we do it right, we can combine test and process improvement to reduce the total time taken for tests. Now, this might not make sense to you just yet, but there's an amazing article on MS Docs that explains all this in greater detail. You can find it by searching for shift testing left with unit tests, and I highly recommend you to read it. Now, let's go back to our Tailwind Traders website. Now, in the current design, it's a .NET application with some React components on the front end. They run this app on Azure App Service, a PaaS web app service, which uses Docker containers in the back. Now, containers, hopefully you already know them. That means we have our app in a layer of isolation, which runs on top of the host OS and hardware. This is used to host multiple applications in the same hardware and host OS. Compared to VM, containers are much lighter. If VMs are like hotel suites, the containers are like kind of the capsule hotels you might see in Tokyo. The current app is monolithic, means all the backend services, all the functionalities are packed together in one place, one common code base, and one application instance to be deployed and running. In addition, they run Azure SQL Database and Azure Cosmos DB to serve data. Now, this worked great initially. However, Tailwind Traders began to identify the limitation of monolithic design. They want to decouple their sub-resource APIs so that they can maintain and improve code quality on each part. Now, to decouple means to separate the parts that are closely dependent on each other. There are many benefits of doing this. Example, dedicate a specific team to each modality, and you can fix each part independently, and a part can scale independently. But the biggest concern is quality. How to keep software free of bugs and issues after they implement these changes. And they want to have a sense of confidence while implementing such changes. This brings us to the third point, security. If we can enforce security while implementing the changes, this will improve our quality and our confidence too. Now let's take a look at how we want to change the Tailwind Traders website. They want to change the website to what we call the microservice architecture, which means they need to divide the one single code base and app instance into smaller services, each working independently as a service and has an independent endpoint. In case of Tailwind Traders, they came up with 11 different microservices, in which 2 of them are Gateway APIs for mobile and APIs for web app front. All microservices still communicate with Azure SQL Database and Azure Cosmos DB. Now, one of the challenges is how to manage security and vulnerability. Now, these days, it's normal to have hundreds or even thousands of open source dependencies. This brings us to new challenges. Imagine you have a code that installs 5 packages because of the norm in the open source world. Many of them have dependencies on other packages and more if you track up. You may be able to track the 5 that you choose to install, but can you track all the dependency trees here? And what happens if one of our upstream dependency has a vulnerability? That can mean that our whole project is now at risk. So now, where should we fit security into our development lifecycle? In pre-commit, we can do something like threat modeling. That means understanding what threats are possible. Use plugins in IDEs and pre-commit hooks. Do peer review for the code, along with coding standards, which can be implemented in the project config. During commit, do a static code analysis, which basically refers to scanning the code as text and looking for errors and style problems. Run unit test or manual test on the running code. Look for danger in dependency. Do something like credential scanning or secret scanning. In deploy section, check items during commit once again. Look at infrastructure as a code segments, which are necessary for identified abstracted layers of infrastructure. Run cloud configuration checks, run security acceptance tests. And after deployment, set up monitoring, threat intelligence, example DDoS protections and firewalls, something we'll discuss more in the module 5. We also do additional postmortems where we reflect on the development cycle for the lessons that we learned in the past. Now, specifically in the case of Tailwind traders, we need dependency insight, which checks the dependency inventory in real time. We also need to see if there are any known risks to open source packages, so we need to fix or remove them. It also adds license compliance to the project. Secondly, we need vulnerability management, which provides code scanning and secret scanning, which can be also automated with security updates to fix these vulnerabilities. Finally, we can use CodeQL, which is the world's most advanced code analysis system. It includes a vulnerability hunting tool, and we can take advantage of its top security experts community. Now, GitHub provides a powerful suite of security tools known as GitHub Advanced Security. The table here summarizes the availability of GitHub Advanced Security features on public and private repositories. All GitHub Advanced Security features, except for the security overview, are enabled by default for all public repositories on github.com. To access the features on private and internal repositories, you need a GitHub Advanced Security license together with your GitHub Enterprise account. The features include code scanning, which automatically detects common vulnerabilities and coding errors. Secret scanning, which receives alerts when secrets or keys are checked in, and excludes files from scanning and define up to 100 custom patterns. Dependency review, which shows the full impact of changes to dependency, and see details of any vulnerable version before you merge a pull request. Then we have security overview, which reviews the security configuration and alerts for the organization and identifies the repositories at the greatest risk. Now let's take a look at basic security scenario. Now this slide illustrates a traditional security as a gate approach. We do some testing when we merge PR, example to test if the app still works after the merge or not. But more importantly, we have a phase dedicated to quality assurance. The CI, that is continuous integration or testing phase, where a single or a series of security tests takes place. In this scenario, a security often ends up being a bottleneck in our delivery because they're bulky and now too late in the process to stay flexible. And because it is the only stage that you depend upon for quality checking. This is why you want to move left. Now in GitHub, we have something called GitHub Advanced Security that can really help us out. It has security policies that allow you to set up security from the very beginning and can be included in the project configuration. It has code scanning that scans for potential vulnerabilities and coding errors at every merge and commit. It has secret scanning that scans for credentials, example tokens and private keys that might have been accidentally included in your commit or PR. It has dependency review that keeps track of project dependency changes and their impact on project security. The project dependency tree will be compared to GitHub's database of known vulnerabilities at every PR. Then we have security overview, which offers administrators a high-level view of project security status. This enables them to identify problematic repositories that require intervention. Now, when it is time for quality assurance, the security of your code has been reviewed multiple times. Now, there's a less chance of bottleneck and less chance of technical debt, because all the earlier checks have fixed the problem in the code. Now let's take a look at these features of GitHub's advanced security features in much more detail. First, vulnerability management. Now NIST estimated that the cost of fixing security defects in production can be up to 60 times more expensive than during the development cycle. GitHub's vulnerability management provides you 62 million security alerts that are sent across GitHub at any given time. These alerts help us better understand the potential threats affecting our code base. Now, GitHub's code scanning allows us to find and fix vulnerabilities before they are even merged into the code. As mentioned before, we can accomplish this using code QL scans, which will help us to find and fix vulnerabilities really fast. Code scanning uses a community-driven query to empower every project, thereby backing every project with a world-class security team. The best part of code scanning is you can easily integrate your security results directly into your developer workflow. This provides a frictionless experience and faster development. Now, next we have secret scanning. Here, a secret is any kind of secret information that your app might use. If your project talks to an external service, you might use an authentication token or a private key to connect. Now, if someone accidentally includes a secret into the repo, anyone with read access to that repo can access the external service. Meaning, if you have a database with all your customer data inside, anyone who can see your access, your repo, can see it. You may think this won't happen to me, but this has in fact happened many times before as security incidents. Secret scanning is enabled by default on all public repositories on GitHub with this feature. If someone checks a secret with a known pattern into a repository on GitHub, it will be caught immediately during scans. A repo admin will get a notification, and they can quickly view all detected secrets into the security tab. But when do these secret scanning happen? Now, if you enable a feature called push protection, secret scanning will check high confidence secrets, which means those identified with a low false positive rate. This happens when anyone does a push to the repo, so you can prevent anyone from pushing secrets into your repo. Now, secret scanning also lists any secret it detects. The author can review the secrets and remove them, or choose to bypass the check. If a contributor bypasses a block for secret on GitHub, GitHub will immediately generate an alert, create an alert in the security tab, adds the bypass event to the audit log, and sends an email alert to all the admins with the link to that secret and the reason for it. Now, GitHub's advisory database. It is a database for all your dependencies. It contains info on vulnerabilities in open source, including third-party solutions. Remember the chain of package dependency? This is the tool that helps you to be safe, even when using an open source package. The database is curated by a dedicated team and tracks dependency trees by dependency graphs. Security threats are ranked from low to critical. GitHub updates this list regularly using an authoritative source, such as the National Vulnerability Database and the NPM Security Advisory Database. Now, another great feature is Dependabot. Imagine a project that includes 20 to 30 third-party packages. Manually monitoring the status of these packages and keeping them up to date is really hard. Dependabot is GitHub's answer to this challenge. It checks the project's manifest file, which outlines the project's dependency tree. Next, Dependabot checks the GitHub's advisory database to see if any update show packages we use are flagged as out of date or vulnerable. If there's an issue with anything in our dependency tree, either installed by us or indirectly used, Dependabot sends an alert to all team members. If none, push reviews can be automated. If yes, the alert can be reviewed for further decision. This helps avoid maintenance oversight. Now back to Tailwind traders. They've had some success migrating to a microservice architecture, but there have been some security incidents. They've identified the problem as vulnerable container images, missing settings, passwords in database connection strings where secrets were baked into application images. The stakeholders are kind of worried now. What do we do? Now we've known GitHub's advanced security can help us in a few ways. It has code scanning to help us with code quality check enabled by code QL. It also helps us to scan common vulnerabilities in Docker images before pushing them to a container registry or deploying to a Kubernetes cluster. We'll take another look at containers and Kubernetes later. Now that you can't commit any secrets into the repo, you can manage secrets in a cloud-based service like Azure Key Vault, which can be pulled into your workflow very easily. Now it's time for a quick demo. The Tailwind Traders technical team is settling on the new tooling. Work is moving across their boards, as we have learned in the previous module. And now we're starting to get a sense of accomplishment after looking at these boards. Unfortunately, all is still not well. There have been several instances when new releases were deployed with vulnerable container images or missing settings flat out. In fact, in certain instances, we found passwords and database connection strings and certain secrets were embedded and baked into those application images as well. The team's leadership is also worried that since we are now moving at a very quick pace, and since we are now able to sprint that much faster, Are we really taking the time necessary to review our code as thoroughly as we need to? Or are we sacrificing code quality and doing defensive coding in the name of cycle time and just trying to hit that deadline? In an effort to address these concerns, our team is going to investigate what we can do. We've identified the first step. It's to run the security features inside of GitHub. By turning on dependency alerts and things like code scanning, we're able to target two serious problems that we have. For one, we target outdated dependencies. Two, we also target common security practice violations in our code. We can couple that with Azure Security Center and vulnerability management for scanning container images, and thereby enabling us to be more proactive in our mitigation response. We can also use Azure Key Vault for our cryptographic keys, certificates, and other sensitive secrets. Azure Key Vault allows us to store, access, and manage the rotations of those secrets in a secure and controlled fashion. Now let's walk through the basics of how easy it is to add these GitHub security features that I've mentioned. We'll also walk through Azure Security Center, vulnerability management, and we'll even take a quick look at how easy it is to rotate secrets using Azure Key Vault. Now, you've seen Tailwind traders before in previous modules, but things have changed since you last saw a storefront. We took a leap and jumped into wonderful world of abstraction and microservices. Our previous application architecture utilized both .NET and React as a part of monolithic application running in Azure App Service. And while we still utilize both .NET and React, we added Java and Go and decoupled our application into 11 different microservices now running in Azure Kubernetes service. We did this to help us to sprint and move faster, rather than having to update our entire application for a single change in backend API. We can just update that one API. However, this architecture changes comes with a great responsibility. For one, we must be aware of any vulnerabilities, not only in our code, but our 11 different application container images. We are currently looking at Tailwind Traders backend project repository. If we drop down into the deploy folder, you'll notice we have a folder named Helm. Now, Helm is a de facto package manager for Kubernetes, and this folder holds the declarative syntax for what each component of our application needs. We use Helm to easily deploy each one of our Tailwind Trader services. We can see that we have the cart API, the coupons, the image API, and more. Now, heading back to our project's root folder, and we look into the source folder and drop into services. And we'll see what also we have for a code that lines up with the same services that we saw in our Helm folder. This is a lot. We need to scan everything in here with GitHub's code scanning and dependency scanning. There are a few ways we can get started. First, we can click on the Security tab. What we can do is set up a security policy. Your project security policy will define how users should report security vulnerabilities. What I really like is when you click on Setup and then Start, it gives you a nice little markdown sample that you can preview. Heading back to the Security tab, after defining the security policy, you can take advantage of security advisories. Now, this report doesn't have any, but I want to show what security advisories look like in the context of a real-world project. Let's take Helm for example. It's an open source project. We have companies around the world that contribute to this project, and as a result, it's also an area where there can be a great deal of security concerns. We can see which security advisories exist for Helm, and there are 9 at the moment, ranging from low severity to high severity. If we drill down into one of these advisories, you'll notice that Helm identifies which package contains the vulnerabilities. Helm indicates which versions are affected and which versions have been patched to address this vulnerability. You'll also notice you can define the impact of vulnerability and any known workarounds and packages. Now let's head back to Tailwind Traders backend project repo and check out what other security features we have access to. The third feature that we can enable is dependable alerts. And dependable alerts will notify you when one of your dependencies has a vulnerability. Let's click and enable, and you may notice that GitHub has routed us over to Security and Analysis tab in our project settings. You can enable features in GitHub by either clicking on the Security tab itself, or you can add additional features under the setting. Here, you'll notice that I have 2 choices with Dependabots. I can enable the alert themselves, and I can opt to enable security updates once those vulnerability packages have been found. Enabling Dependabot security updates allows GitHub to open a PR with a patched version of your dependency after an exploited dependency has been found. The last GitHub feature that you can configure is code scanning. Code scanning will automatically detect common vulnerabilities and coding errors, which will help us to be more proactive as we develop. Here at Tailwind Traders, we have already configured this feature. Now, code scanning works hand in hand with GitHub Actions, and we'll learn a little bit more about GitHub Actions in a final demo in this module. Now that GitHub's native security features have been enabled for our Tailwind Traders project, what happens after we've updated our code and dependencies, performed all the scans, and built our application images and pushed them into Azure? From within our Azure portal, we can navigate to Container Registry, then click on Security tab on the left side. From there, you can immediately see which recommendations exist for our repository. A description of the issue and the severity level can be seen as well. We can click on any one of these to get more information. Clicking on the top option will allow us to see vulnerabilities detected in our container images. Here, we can see that we have 3 findings that apply to our various number of application images. Again, we can drill down to any one of these findings to see more information, including remediation suggestions if available. I also have the option to take action right from within Azure portal. By clicking the button to take action, I'm directed to bird's eye view of different repositories within my Azure Container Registry. I can clearly see that there are 9 unhealthy repositories and 2 healthy repositories. That equals to 11 microservices that I previously mentioned. You'll also notice that we have column labeled CI/CD critical findings. Remember, CI/CD stands for continuous integration and continuous delivery. This column allows us to trace the CI/CD GitHub Actions workflow, build the image in question. At this time, we can see Tailwind Traders has not yet enabled this feature, but we'll learn how to do that later today. Finally, the last thing that I want to show you is Azure Key Vault. From the Overview tab, you can see some helpful getting started guides, as well as some monitoring insights which showcase metric data for requests, latency, and more. Now, what's really important is on the left under settings. You'll notice a variety of settings. The top 3 focus on the type of secret information you can store in your Azure Key Vault. Let's get started with keys. Then you can generate or import existing keys for your project. Let's take Tailwind Traders Postgres key for example. Drilling down into keys doesn't reveal any sensitive information. Instead, we can see that the key identifier when the key was activated, when it expires, and if it was enabled. We can even see which permissions this key has been granted. Now let's take a look at secrets now. Here at Tailwind Traders database secret, this holds a connection string to one of our databases for Tailwind Traders application. Drilling down into secret, again, I will see an identifier. And I can still configure activation dates and expiration dates for this connection string. Finally, let's look at certificates. Again, like keys, you can generate new or import existing certificates. Here's a cert we have for Tailwind Traders, where you can see the same activation and expiration settings we saw in keys and secrets, the same control to enable or disable the certificate, and the identifier we can use within our application. This is very important for security for all applications, but in case of Tailwind Traders, we found this to be a lifesaver, particularly because we have so many different services for our online storefront. By setting activation dates or expiration dates, I can update the database string for 10 different APIs at the same time, since the connection string itself is stored in the key vault. Now let's take a look into our container security. Now at Tailwind Traders, we have identified several microservices. We choose to run them on something called as Kubernetes. Now what is Kubernetes? Now Kubernetes is an open source technology used to manage and orchestrate workloads on up to hundreds or even thousands of containers. Here we choose it to run our microservices. Now Kubernetes works in 2 ways. This slide shows the self-managed scenario. In self-managed scenario, you are responsible for everything. The control plane, the agent pool, the upgrades, and the API endpoints. Kubernetes is a very complicated topic, and we can't explain everything in detail here. There's another great article on MS Docs called Kubernetes Core Concepts for Azure Kubernetes Service, which is highly recommended if you want to know more. To cover the bare minimum needed in this session, let's take a look at few key terms. Pods. Now, one pod is used to run one app instance. One pod can be one container or collection of multiple containers. Agent pool or the worker nodes. These are the servers that run your containers in the pod. Think of them like managers to your actual workers in the team. Then we have Kubernetes cluster, which is something made up of multiple nodes with different roles. Example, the control plane node, worker nodes, and so on. Now, when you deploy, you define what your application needs to run on, and you hand it off to the Kubernetes API endpoint. Your control plane manages these nodes through features like Kubernetes API, scheduler, cloud controller, controller manager. Anyway, we don't want to get into too much detail here. The idea is you need to configure the control plane because it does things like assigning pods to worker nodes, like manager to the team. And there's a lot to manage. On the other hand, you can use the Azure Managed way through AKS. The Kubernetes control plane is completely managed by Azure, and you're freed from most tasks related to control plane. Do notice, you as the user is responsible for Kubernetes worker nodes, such as agent pool, like OS patching. Now, let's refresh on containers. Now, when container actually builds up an image, it does so like layers to a cake. You put a sponge cake, then cream, then fruits, then more cream. We need to be very careful and aware of what we bake into our cake. Now, what happens if someone puts a rotten strawberry inside? What happens if someone puts a key inside it and someone eats it? Now, let's take a look at it in a quick demo. Here we have Tailwind Traders' full CI/CD GitHub Actions workflow. This is the workflow Tailwind Traders uses to deploy our application to various environments like dev, staging, canary, and ultimately production. We have three main stages or jobs within this workflow. The first stage or job deploys our infrastructure. You'll notice that there are a handful of steps involved in standing everything we need. The reason we are able to keep this stage so simple is because that we've utilized Azure Bicep to declaratively stand up the resources that we need. Azure Bicep is a domain-specific language used to define the desired Azure configuration. And it works by letting the Azure Resource Manager provision what has been defined. What's neat about Bicep is the deployment isn't only standing up our infrastructure, it is simultaneously ensuring our infrastructure is in alignment with corporate policy as well. It's accomplishing this by deploying Tailwind Traders' Azure policy definition and assignments right alongside our other Azure resource objects like Azure Kubernetes Service, Azure Container Registry, Azure Key Vault, our database servers, and so on. Once our infrastructure has been provisioned, we can proceed to our next stage or job. This is the stage where we build the images we need for Tailwind Traders. You can tell what each step in this stage is doing by the name of the task. We are checking out our code now, and we are building a Docker image for each individual API. Once our images are built, we also push those images into our container registry that we previously saw. The final stage is our deployment stage. This stage handles the delivery of our applications to our necessary environments. Similar to the build stage, you'll see a step for each one of our microservices. You'll also notice, as I mentioned earlier, we are using Helm to deploy our application to our Kubernetes cluster in Azure. Our current workflow works well and deploys everything we need for Tailwind Traders storefront. But as we saw in our last demo, we have vulnerable images in our container registries. And we have zero insight into which CI/CD workflow pushed those compromised images. Now let's take a look at how we can wire up the CI/CD critical findings and get even greater traceability into the health and security of our application. I'm going to start from my preferred IDE, the Visual Studio Code. I have my Tailwind Traders backend repo up, and I've opened up my pull request workflow YAML file for my card API service. This is the workflow that fires off every time a pull request is open with a change to that service. As a part of the defined steps, we build our Docker image, push it to Azure, and then deploy this single service into a PR namespace on our development cluster. We'll learn more about it later today. For now, I want to add in two steps. The first step, I'll add in a scan image task right after we build our container image. This will allow us to get scan insights directly from within GitHub as to health of our image. After the scan is complete, we'll push the image to Azure, and we'll add our second step. This step will publish our container scan results to Azure Security Center. That's it. Those are the only two modifications needed to wire up GitHub Actions to Azure Security Center for container images. To test this, I'm going to check in some changes I've already made to the card API. You'll notice I'm doing all this from Visual Studio Code, including opening a pull request. Now, opening a pull request is what will trigger this updated workflow. Let's check on the progress. Awesome. I can see our workflow is running, and it's just about complete. Perfect. It completed successfully. Only now I see a red cross on the left hand side. When I click on it, I can see the container scan results right here as part of my build report. I can see the specific vulnerabilities contained within this image. And I'm even informed of best practice violations. Based on this information, we can make actionable decisions to mitigate these concerns in our next sprint. Heading over to Azure Security Center and drilling down into the cart API repo within our container registry, I can clearly now see CI/CD scan has been found for our recent push. Drilling down into the scan report for this image, I now see the same insights here in Azure Security Center as I do in GitHub Action Container Scan report. In fact, when I hover over to the icon to the right of CI/CD scan findings, I see CI/CD pipeline info including deep links to the repository, the run, branch, and even the commit. This is fantastic. Now we have only implemented this report for this particular PR workflow. But now we can take steps that we have learned and enhance our full CI/CD workflow to give us the same traceability that we have for our pull requests. All right. Now that we have learned a lot about security resources, we can take advantage of it. Let's take a deep look at how to develop with quality when working with microservices and Kubernetes in a real demo. Now, let's complicate this a little. What happens if you need to debug one microservice in the context of your larger application, or in the context of abstracted services running in Kubernetes? Have you ever wished you could just take your computer, just put it into the cloud, and debug as you would locally, especially if you're only debugging one small part of your app? Our final demo will focus on something called Bridge to Kubernetes, which will let you do exactly that. We're going to pick up from where we left off in our last demo. If you recall, we opened a pull request with changes to our cart API service for Tailwind traders. Now we've all been there. We've all made changes that we were 100% confident in. We have linted, we have tested, and all that jazz. At some point in the process, after we merged our changes, but before those changes deployed to production, we noticed, something broke. Oh boy, did we just merge broken code into our main branch? Wouldn't it be great if we could visualize our changes prior to merging it into the main? It turns out we can. Taking a look at our open PR, you'll see that we have utilized a GitHub action task to add a comment. Between the comment bot and Kubernetes, we can take advantage of RBAC and namespaces to create an isolated deployment environment for our PRs. Now let's take a look at these changes now. So far, everything looks good. Let's log in here and we'll add an item to our cart. Remember, the service we updated is our cart service. I'll navigate to Home Appliances. Great, that loads. Now let's add microwave to our cart. I'll click on the item and hit add to the cart. Something doesn't look right. If I'm not mistaken, I just saw a pop-up saying Red Garden Gnome was added to my cart. Let's check out our shopping cart. Sure enough, there's a single Red Garden Gnome there. I'm going to have to debug this. Now, if I want to debug this locally, I know that I could stand up everything, all 11 services, but I don't have time for that. I'm going to, in essence, put my computer in cloud so I can debug in real time in an isolated fashion. Now, you may be wondering, how exactly are you going to do that? And I'm so glad you asked. I installed an extension called Bridge to Kubernetes that allows me to replace the provider code currently running in Kubernetes in my private namespace with the code on my system. Best part is, I don't have to deal with Helm charts or Docker files to do it. Once I have the extension installed in my system, it's actually very simple to use. All I have to do is hit Command Shift P because I'm on Mac. If you're on Windows, you would hit Control Shift P from there. I'm going to search for Bridge to Kubernetes. I'll opt to Configure. Now, as long as I have access to my Kubernetes cluster that I'm working in and the namespace that I've deployed to, this extension is going to connect over to my application currently that is running in the Kubernetes cluster. I'm going to choose the service I want to actually redirect traffic to. Again, this is going to allow me to replace the broken service with the code that's living on my system, so I can debug natively. You'll notice that we have several services here, all corresponding to our microservice APIs. I'll choose the cart service since that's the one I want to debug. I know my application is listening on port 3000. Next, I'll choose Launch Program. This is going to launch the same configuration that I would use to debug locally. but it's going to launch it with an additional task, and an additional task will connect to our Kubernetes cluster. Finally, I'm going to select the option to redirect requests to a subdomain prefix. The subdomain prefix will create an isolated version of our cart API, while allowing access to other services required for cart API to work, without having to deploy those services. Now what that did is update my launch configuration with a new configuration to allow me to debug using Kubernetes. Now I can go over to my debugger, make sure that my launch program with Kubernetes is selected, and hit F5. From there, the bridge to Kubernetes extension is going to do all the magic for me. It's going to redirect the cart service to my computer with an isolated subdomain prefix. And a better way to visualize that is, I'm literally putting my computer right now in that namespace, in my Kubernetes cluster in the cloud. Great, my debugger is up and ready to go. I'm going to open our shopping cart JavaScript file and set breaking point to line 52 and 53, since this is our add item method and the garden gnome seems to be adding to my cart when I add any item. Now let's go and add item again and see if we hit our breaking point. Yep, we sure did. And I have access to watch window, my call stack, and I hover to line 52 here. You'll notice I even have IntelliSense. Now I'm going to step through here and see what comes to our doc object. Checking my call stack, I can see add product method is being called in a different file. I can continue to step through my code, just as I would with your typical F5 development experience. I think I see the problem here in the add product method. It looks like someone hard-coded a body const to return a red garden gnome every time. I wonder who did that. Okay, I'm gonna fix this up and we'll check this in. Now thanks to Bridge to Kubernetes, I'm 100% confident that this will work. I'm going to stop my debugger and head over to GitHub to check out what's happening with the pull request. Great, it started our PR workflow again, and while that's running, let's take a closer look at the steps that are running. We've already reviewed part workflow in our last demo, but let's see what happens after we publish the scan results to Azure Security Center. We'll log in to our Azure Kubernetes cluster, and we'll do so using a native GitHub action. This means we don't have to copy and paste any config files or store any additional secrets. GitHub can handle authentication for us. We'll generate a valid namespace for use with this pull request. This is the name we'll use for PR release. We use Helm to deploy the single cart API chart. And we add some routing labels and annotations so that the routing manager, now living in a cluster that was deployed from Bridge to Kubernetes extension, can route traffic according to this pull request. Finally, the last bit of magic is adding a comment, or a dash of confidence as I like to call it, to the PR with a link to go view these changes. This saves us from accidentally checking in broken code into our main branch. Let's flip back over to our pull request and take a look at the conversation. Sure enough, I can see now that I have a new comment with the same new link. I'll click that and let's check it out. We're still signed into our store, and I'm going to try to add that microwave again. It looks like it worked. I'll just verify what I've seen in my shopping cart. Excellent. I now see a microwave rather than that silly garden gnome. Thanks to Bridge to Kubernetes, this is working exactly as expected. Now, how do we bridge to Kubernetes with all that we know so far? We know that with managed Kubernetes, a microservice development can be simplified because it helps to eliminate the need to manually source, configure, and compile dependencies. It can reduce operational complexities of building and deploying the code into a cluster. Lastly, it helps developers to work in isolation with a shared development environment. There is no need for each developer to individually configure the control plane. The operational tasks like scaling are now managed at a cluster level. Each team or developer can work in a private sandbox environment in isolation by routing specific traffic locally. Now, this is an overview of GitHub's Actions architecture. We won't go into too much detail here, but you can see that it is connected to different services we depend on, such as the SQL database, Cosmos DB, and GitHub. Now, the GitHub Actions help you to automate the process of build, deploy, and it allows you to do so with confidence. Also, it's highly customizable. We'll discuss in more detail in another module. Now, a quick recap on what we've learned. We've learned about code scanning and dependency alerts. We learned how we can build more using secure containers. And finally, we learned how we can gain DevOps confidence for our entire team and ensure everyone is confident in the quality that we've built. Now with this, we come to the end of Module 3. Thank you for your attendance so far, and we look forward to seeing you next time for part 2 of this session, the Microsoft Azure Virtual Training Day, DevOps with GitHub event.